Hello everybody and welcome back to part 2 of exam 2. Today we're going to be covering everything else that I didn't get to last time that was on the first slide, and we'll start that off with milliosmoles. So you may remember that we finished with milliequivalence last time. The formula for milliequivalence was millimoles times valence. Milliosmoles are different in that it's millimoles times ions. So what does that mean? Well, it's not always necessarily an ion, it could just be a substituent of a solution, but it's basically, when I use the word ion, I kind of mean how many parts is it going to be in a solution. So I brought up some examples here, and I just want to work through them with you. So for NaCl, there's two components, right, that'll break apart. There's Na and there's Cl. So for this, there's two ions. Calcium chloride. You can see that there's two chlorines attached to that calcium, so there's actually three here because there's one calcium and two chlorides. Calcium carbonate, even though this O is a 3, the carbonate ion doesn't break apart, so there's actually only two here because it's calcium, and then carbonate will dissociate from calcium, but it won't break apart into carbon and oxygen. Same idea with lithium carbonate, two lithiums, one carbonate, 3. Sucrose. Sucrose does not actually break apart in water, and that's just something you kind of need to be aware of, is that sugars really won't break apart generally, unless they're really strange. So this is only one actually. Sodium acetate, we have one sodium and one acetate ion, so that's 2. And we have mannitol. Mannitol is another sugar, so it's just 1. So not too bad. It's basically all you need to be able to recognize is some of those more complex functional groups like carbonate. Not super duper hard, but just be aware of that. So even though like they might be composed of multiple different elements, know kind of which elements will stick together, and a really good way to do that is just know if it's like a covalent bond versus an ionic bond. If it's an ionic bond, it's almost always going to break apart, but if it's covalent, then it'll generally stick together. So now let's work on some math problems. We need to find the number of grams of potassium chloride to make a 200 milliliter solution at 250 milliosmoles per liter. So okay, let's start setting up the problem at 250, and then I'm going to do the same thing I did with milliequivalence. Instead of writing milliosmoles, I'm going to write millimoles times ions, just because it's going to make my life easier, and it should make solving these problems easier. So 250 millimoles times ions, and then that's per liter. And I'm just going to make our life a little bit easier here. Since I know we're going to have to do something with milliliters later, I'm going to put per 1,000 milliliters, because there's 1,000 milliliters in a liter. So from here, what I need to do is I need to just multiply that 200 milliliters out. And then for number of ions, in KCl's, there is one potassium and one chloride. So there's actually two ions, and I put this in the denominator so the units cancel. That's a really good way that you can kind of check your work. Just make sure you're multiplying or dividing. With valence, almost all the, or with milliequivalence, the valence was usually 1, so it wasn't as big of a deal, but definitely you want to make sure you're counting your ions for this, because they'll usually not be 1, unless it's like a sugar. So ions will cancel, and then 1,000 millimole per mole times, I don't know how many grams per mole are of potassium. I think it's, part of me wants to say it's like 74.5. Does the problem tell us anywhere? No, of course it doesn't. Now I'm like scanning the other problems I have on here. Okay, well let's pretend for the sake of this problem that there are 74.5 grams per mole of potassium chloride. I'm pretty sure that's right, but and that's something Hegner will give you on the exam, so don't worry too much about that. I guess it just wasn't included in this problem. So we have 250 divided by 1,000 times 200 divided by those two ions divided by the 1,000 millimoles per mole, and then times 74.5 grams per mole. And with that, we get our final answer of 1.86 grams of potassium chloride. Not too bad, just a lot of dimensional analysis, but it's very similar to how you solve milliequivalence. How many milliosmoles of calcium are there in a solution that contains 8.75 grams of calcium chloride? Okay, so this one's interesting, just because it's solely looking for our milliosmoles of calcium. Basically, the key to this problem is knowing that there's 3 milliosmoles total, or like a solution will contribute 3 milliosmoles of ions, based on the fact there's 2 chlorides and 1 calcium. So we can begin getting started with this. So if we start with our 8.75 grams times, we will need a molar mass for this, so we'll do 40 for the calcium and then 35.5 times 2 for the chlorides. That's 111 grams in a mole times 1000 millimole in a mole. And then 3 ions total in this solution, but since we're just looking for calcium here, we can actually just make this 1 ion. We can shortcut it because we basically multiply by 3 just to divide by 3 right after. So I'm just not going to write that out. So 1 ion of calcium in this solution. So 8.75 divided by 111 times 1000. And you find out that there are 78.83 milliosmoles calcium in this solution. Not too bad. Milliosmoles, similar to milliequivalents, are additive. So basically, we can have more than one thing in a solution that can contribute to its osmolarity. So that's exactly what this problem does. It wants us to find the osmolarity of a solution that has 2.5% dextrose and 0.45% sodium. And it wants us to basically verify that this osmolarity is 280. So how do we do that? We can start off with our, we'll just start with the sodium. So since it's a 0.45% solution, that means there are 0.45 grams per 100 milliliters. And then we could just multiply this by 1. Is this the best way to solve this problem? There's a few ways you can go about this. I'm actually gonna... No, I actually like this way. Yeah. So 1000 milliliters in a liter, right? Because we want our final thing, since we're verifying, we want our final answer to be in liters. And then we need to calculate our grams per mole of sodium. So with sodium, it's 23 plus 35.5, that's 58.5. 58.5 grams per mole times 1000 millimole per mole, and then times our 2 ions, because sodium and chloride are each their own ion. 2 ions. Dextrose is a little bit easier just because it doesn't break up into ions. So we know for dextrose there's 2.5 grams per 100 milliliters because it's 2.5% times 1000 milliliters in a liter times, it doesn't give us the mass of dextrose, which is a little bit obnoxious, so we have to calculate it out. So it's made of carbon, oxygen, and hydrogen. It looks like there are, oh, and it's 1 hydrate as well. Awesome. That makes our lives even easier. So we know there's 6 carbons, so that's 6 times 12, plus 12 hydrogens, which are each 1, so that's just plus 12, plus 6 oxygens, so that's 6 times 16, plus 18 because there is 1 water attached to it. And the way I got 18 is oxygen 16 plus 2 hydrogens is 18. So we get that there are 198 grams per mole of dextrose, and then we multiply by our 1000 millimoles per mole, and then we just multiply by 1 ion, which you don't technically need to do this step. I just like making sure my units line up at the end, so that's why I always write it out. But with this, we should have everything, so let me just plug it in my calculator. So 0.45 times 1000 divided by 58.5 times 1000 times 2. With that, we get Oh, and divided by 100 at the very beginning. So we get 153.8 for the sodium. For the sodium and chloride, I should say. And a way that you can kind of verify this later is at one point in your pharmacy career is you'll need to know that the milliequivalents of like normal saline. This will be a little more important for your therapeutics eventually. Um, Normal saline has 154 milliequivalents of sodium alone. However, since this is sodium and chloride, it's kind of like, even though it's half the strength of normal saline, which is 0.9%, if you were to double it, it'd just be equal. So that's actually a really easy way we can check our first step. So it looks like we're on the right track so far. So then it's 2.5 divided by 100 this time first, so I don't forget. Then times 1,000 divided by 198. Then times 1,000. We get 126. So we can add our 126 to our basically 154 we just got, and we did get 280 when we did all that. So this was like 154, and this was this other one was 126. So basically at the end we did verify it. So that's good, and that's how you'd verify it. You basically just add up the components. For this final one, a solution of calcium gluconate. Gluconate is a pretty uncommon molecule. Oh, it actually gives it to us. Yeah, so it's a -1 charge, so there's 2 of them attached to every calcium. A solution has 25 milliequivalents of calcium per liter. What is the osmolarity of this solution? So this one may look a little complicated. It might look like we have to do a ton of math. We actually don't, because basically we know since there's 3 parts to this solution, there's 1 part for the calcium and then 2 parts for each of the gluconates. We know there's 3 total parts, and since they all contribute equally, if there's 25 milliequivalents of calcium, that means there's also going to be 25 milliequivalents of each gluconate. So we have 25 of the calcium plus 25 for the gluconate, but since we have 2 gluconates, that's times 2. So our answer is actually just 75 milliequivalents here. Pretty simple. Not too bad. Okay, so this next concept, in my opinion, isn't too hard. I'm kind of surprised it doesn't fall earlier in the course, just sequentially. It's basically just teaching about different kind of ratios of specific ingredients to each other in usually compounded solutions. You could probably have one of these problems without compounding, but this is just, it makes a little more sense for the problems to revolve around compounding. So let's just jump into it. For this first one, we're making 1,000 milliliters of this solution, but it wants to know how many of each of these ingredients we need if we only made 8 ounces. So if you remember, there's 30 milliliters in an ounce. Multiply that by 8, we get that 240 milliliters. So we're basically finding out how many of each of these ingredients we need to make per 240 milliliters. So a really easy way we can do that is just by setting up a simple fraction. If 1,000 is the normal total, we can just put 240 over 1,000 and then just multiply by each of these ingredients. So I'll do that really quick in my calculator. So 240 over 1,000 times 40 grams of ferrous sulfate, we would only need 9.6 grams. 240 divided by 1,000 for our citric acid, which is only 2.1 grams. Instead, we would need 0.5. $240 over 1,000 times 2 milliliters of peppermint spirit. We'd only need 0.48. I apologize, my handwriting's really bad all of a sudden. Well, not that it's usually good, but 240 over 1,000 times 825 is only 198 grams of sucrose. And that's pretty much it. That's just how you solve this. So not too bad at all. For this next one, it's ingredients might be expressed in like parts of a whole. That's kind of what we just did in a way. But we know that we can like set these up as fractions, right? So basically, how many parts do we have total? That's the first step to solving any of these. So we basically need to add our parts. So we have 0.5 plus 4.5 plus 35. So we have 40. 40 parts total. And we know that, for example, 0.5 of those 40 parts are salicylic acid. And that's how we'll set it up for each problem. And we're also looking to make 1,000 grams of this ointment. So basically what we can do is, since we know that we know our final mass, we can literally just set up these ratios. Since we know that 1,000 is the total gram, and this is the parts per the total amount of grams, we can just do times 1,000 grams. And this is our salicylic acid. So I'll do this for each one of these. So 0.5 divided by 40 times 1,000. You need 12.5 grams of salicylic acid. For the ppP sulfur, 4.5 over 40 times 1,000. And that gives us 112.5. And then finally, for the 35 divided by 40 of the hydrophobic ointment, we have 875 grams. And I didn't write out that last one, but it's the same process. And a really easy way to check yourself is just make sure these all add up to 1,000. They do, so perfect. That's all you need to do for that problem. This next one, determine the amount of rifampin needed to compound the following prescription. This is kind of an interesting concept that I think a lot of people take for granted, at least before they come to pharmacy school. This next problem shows it off a little bit better, but basically, when you have a pill, let's just say you have a 10 milligram pill of something, the pill itself probably isn't going to weigh 10 milligrams. In fact, it won't. It just won't. Because that 10 milligrams is only measuring the amount of drug that's present in that pill. The tablet or capsule itself will actually have some weight of its own. And that will contribute. So for example, if you're weighing out a pill in a compounding pharmacy, you'll need to kind of know that ratio of average pill weight to this weight. And I can just kind of show that off in the problem. But it's just important to know that only your active is measured in terms of weight whenever it's talked about. So what does this problem want us to do? We have 300 milligram capsules of rifampin, and the average weight of each intact capsule is 465. And the reason for that is that the capsule itself has weight, besides just the active. And the average weight of the contents of each capsule is 355 milligrams. The reason this might be is that there might actually be some binders or extended release powder formula stuff may help absorption along with the capsules. So like even in capsules, it's not pure drug. It's going to be mixed with some things. And it basically just wants to know how many of these we need to make 100 milligrams and 8 capsules worth of 100 milligrams. So our first step is to find out how much rifampin we need. And that's pretty simple. We just do 100 milligrams times 800 milligrams. Wow, crazy. So from here, we have a lot of things we can do. I'd say the easiest way to start would be to take our total capsule weight at 365, or that 465, I'm sorry, 465 milligrams per capsule. And then from here, since we know each of our capsules is, I'm actually doing this backwards, so we know that there's 300 milligrams of rifampin. No, I was doing that right. Sorry. I just got a text on my phone and it's distracting me. So we have 300 milligrams of rifampin per the 465 milligrams total. And so what we do is we could basically just multiply our 800 milligrams of rifampin we need And let me plug that in my calculator really quick. 465 divided by 300 times 800 milligrams. So this number right here that we got, since our milligrams are revamp and cancel, this is our milligrams total. So we get 1240 milligrams. And this would essentially mean that we need 1240 milligrams versus the weight of the capsules. But then, like, how many tablets of that? Well, we can actually just divide this 1240 by 465. And with this, we get 2.67. So we need a minimum of 2.67 capsules to make this much product. Obviously, you can't have like 2.67 capsules, so this would be like 3 capsules. When Hegner is just asking for the amount of rifampin in this problem, I don't know if he's referring to the powder inside, the pills, because this is a problem I'm stealing from him. So I just wanted to show you all avenues. So sometimes the problem might just end at this 1240, but if he was to ask you how many capsules, for example, he would want you to round up, and then it would be like 3. So just showing off both of those methods there, and kind of where problems like that can lead to. This next one's a little more cut and dry, though. So determine the amount of amlodipine you'd need to compound the following prescription. We have 10 milligram tablets, but remember, that doesn't mean that there's 10 that means there's 10 milligrams of amlodipine. That doesn't mean the weight of the tablet itself is 10 milligrams. And the average weight is found to be 41. So there we go. The tablet itself weighs 4 times more than the actual amount of drug. And the prescription we have is we need a solution of 5 milligrams per milliliter, and we have 4 ounces. So again, the first step to any one of these problems is to start by finding out how many milligrams we need total. If you remember, there's 30 milliliters in an ounce. So we have 4 times 30, 120 milliliters times 5 milligrams per 5 mils. That's basically just times 1, so we need 120 milligrams of amlodipine. Okay, so now we're getting somewhere. Basically set this up like I set up the last one. So we have 41 milligrams total per tablet over 10 milligrams amlodipine. Just put AML times the 120 milligrams amlodipine we need. And this is where your dimensional analysis can really help you, setting up ratios like this, because if we just consider milligrams of amlodipine specifically to be a unit, as opposed to just milliliters, these will just cancel. So basically our final setup is 41 divided by 10 times 120. We'd find out that we need 492 milligrams of tablets, not of amlodipine itself, because for milligrams of amlodipine itself, we only need the 120. And then we could divide this by 41, similarly to how we did in the last problem, just for counting number of tablets. And that'd be we need 12 tablets. That actually divides out perfectly. So depending on what the problem's asking for, if it's asking you how many milligrams of tablets, it would be this. If it's asking you how many tablets, it would be this. So just make sure to know what the problem's asking you for. It can be either. In this case, I think both of them were just asking for milligrams, both those 2 problems we just did, but I did want to show you how to do it with tablets just because I didn't pull one of those problems. So I just wanted you to be aware of how to solve that as well. Okay, so these next type of problems are probably the hardest type of problem in this entire course. That being said, I don't think they're incredibly difficult, but they definitely take a little bit more reasoning capacity, especially because a lot of these problems will be giving you like prescription labels, or like dose instruction labels, reconstitution labels, that makes them a little more difficult. These will work with suspensions almost always. The difference between a solution and a suspension is that a solution, a powder, is fully dissolved and it contributes no volume to the final volume of what it's mixed in, whereas a suspension, the physical dry powder actually will contribute some volume, which will change up the concentration of a suspension. So that's really where the key to these problems comes. So let's jump right into the first one, and hopefully I can demonstrate how to kind of work through these. The label for amoxicillin powder indicates that 68 milliliters of water should be added for a final volume of 100 milliliters. So 100 milliliters and add 68 mils of water. Calculate the volume occupied by the dry powder. First one, really simple. Since we know that the final solution is 100 milliliters minus the 68 milliliters we just added, we get that there are 32 milliliters of powder. Not too bad there. This next one, you would like to make the concentration of the amoxicillin above 205 milligrams per milliliters instead of 250 milligrams per 5 milliliters. How many milliliters of pure water should be added to the amoxicillin powder? So a few steps that we need to take in order to solve this. So since we know that our initial concentration was 250 milligrams per 5 milliliters, and our final was 100 milliliters, we can find out that there were, let me run this through my calculator really quick, 250 divided by 5 times 100, there's 5,000 milligrams of amoxicillin total in that vial. And we want to get that down to 200 milligrams per 5 milliliters. So what we can do is we can set up a proportion here. 200 milligrams for 5 milliliters is equal to 5,000 milligrams over a certain number of volume. So we're going to write that volume as x, but something we're also going to do is we're going to make it x minus 32. And the reason for that is, actually no, we're not. We'll do it because I think I did that backwards. It might be x plus 32, but I can show you how to solve it in the end. We'll just put it over x for now. How many milliliters is this total? So if we basically isolate x, we get 5,000 times 5 divided by 200. We get x to be 125 milliliters, but this is milliliters of the total solution, and we do need to subtract out the powder. So if we do 125 minus 32, we get that we need to add 93 milliliters of water in order to make that solution work. And that's basically just because we wanted to find out how much water we added, not just the volume of the final solution. So a little bit of an extra step, not too bad so hard. These next few probably will ramp up the difficulty a little bit, but I'll show you how to do them. So this next one, it has us read a package. 10 grams of ampicillin, good to know. Use for, you add 94 milliliters. The solution will contain 100 milligrams per milliliter. And it wants us to know basically, and this problem up here is what we're solving for. So how many milliliters of sterile water should be added to the 10 gram vial to make 150 milligrams per milliliter? So right now we have 100 milligrams per milliliter. Pretty standard. This actually wants a more concentrated solution. So we'll actually be adding less than 94 to make this happen. So I think the easiest way to set this up would be, since we know we have 10 grams of ampicillin, that's like our total. So we need to find out how many milliliters 100. I think I just gave the answer. But yeah, how many total milliliters are in the 100 milligram per milliliter solution? So we have 10 grams over an unknown quantity equals 0.1 gram over just 1 milliliter, essentially. So how many milliliters total? We can basically set up this equation to set up each side, isolate x, so we have 10 divided by 0.1 in the end. We see that this final solution is 100 milliliters. This is also something really nice about this unit, is usually both drug manufacturers and Dr. Hegner will want to make sure pharmacists will be adding like a pretty standard quantity. So it'll usually come out to a pretty whole number. But since there's also 94 grams or 94 milliliters of water we added, we find that there's 6 milliliters of powder. So now that we have that, we can finally start to like get into this problem. To get our 150 milligrams per milliliter, we'd essentially set up 150 milligrams per milliliter equals, and we'll set it up with our 10 grams again. So instead of making this milligrams, actually, we'll make this 0.5 grams, 0.15 grams. And then we'll make this 10 grams over x. So basically how much water we should add. So if we do this, 10 divided by 0.15, we get 66.7 milliliters should be our solution, but we need to subtract that 6 milliliters of powder, because remember, this is how much water we need to add. So our final answer is 60.7 milliliters of water would be added to make this. And as you can see, this is less than the original 94, which makes sense. We're making a more concentrated solution. So yeah, that's basically just how we would want to set that up. So for this next one, it's kind of like a multi-part problem. The label on a bottle of ampicillin states that when 128 milliliters of water added to 150 milliliter of an oral suspension, once 128 milliliters are added, we make a suspension that is 150 milliliters, 250 grams per 5 milliliters. And then dose of ampicillin down here is 5 milligrams per kilogram for body weight. How many milliliters of water should be added to mix the dry powder so the child weighing 66 pounds would receive the proper dose in each 5 milliliter suspension? Whoa, a lot going on there. So the best way to do this problem is, because there's a lot of ways you can tackle it. I can think of like 3, but I want to start with just finding out the kid's dose. So what we're going to do is we're going to do 5 milligrams per kilogram is the dose of the child times 1 kilogram is 2.2 pounds times 66 pounds. And that equals 5 divided by 2.2 times 66. We get 150 milligrams. Okay. And that's per dose. So basically what we want to do is, since it wants a 5 milliliter dose, is we want a 150 milligrams for 5 milliliters dose. I'm going to erase some of this work just so we have a little more space to work with. Didn't quite give myself enough room. So that's off to a good start. What we need to do now is kind of what we've been doing, solving for the powder, kind of how it contributes to the solution. So we know that we have 150 milliliter solution for 250 milligrams for 5 milliliters. So what we can do is we can do 150 milliliters times 250 milligrams per 5 milliliters. This is just us solving how many milligrams of powder are in the actual vial. So 150 times 250 divided by 5. We get there 7,500 milligrams in the bottle. So now what we can do is we can kind of set up a proportion for ourselves. And then the last thing is we know, since there's 150 milliliters total minus the 128 of water you add, we also know that there are 22 milliliters of powder, which will come back. Well, it's essentially that last subtraction step. I just want to make sure I included that in there, even though I didn't explicitly say it. This should pretty much always be the first thing you do, is just find out that actual volume of dry powder if it gives it to you like this. But I did want to show that off, just in case, because I know I had to mention that there. So what we're going to do now is we're going to set up a proportion. 7,500 milligrams over x equals 150 milligrams per milliliter. Same thing, solve this proportion really quick. So 7,500 times 5 divided by 150. We get that that leaves us with 250 milliliters added to the solution, but we do need to take away the mass of the powder, or the volume of the powder, so minus 22 milliliters of powder. And we get that 228 milliliters should be added. And this kind of makes sense, right? Since this is a lower concentration, 250 milligrams per milliliter is more concentrated than 150 milligrams per milliliter, meaning we're adding more water. So it makes sense that the 228 is bigger than the 128 before. And again, this is a really nice whole number. Most of these will be whole numbers. So yeah, that's pretty much all there is with those. So this kind of teaches us about military time and like drug dosing, like dose rates, especially with IV. This stuff isn't too bad, especially if you just use dimensional analysis. So let's just hop into it. For this, we want to know flow rate in milliliter per hour if 50 milligrams of drug are in 500 milligrams normal saline, which will deliver 2 milligrams of the drug per hour. So how do we set this up? So this is the formatting I'm going to use for this problem, kind of helps shortcut it. It's a little abnormal, but it just works out because with this kind of thing, you really just want the numbers to work out. So we're going to write 500 milliliters per 50 milligrams. And I know that looks weird, but the reason we do that is so we can have milliliters in the numerator. And now what we can do is we know we want 2 milligrams per hour. Milligrams cancel. We're left with milliliters per hour. So even though we set up that problem in kind of a weird way, it helped our solution a lot. It would save us a few steps. So we can do 500 divided by 50 times 2. We need 20 mils an hour. Not too bad. For this next one, lidocaine infused at 1.5 milligrams per minute, 0.4% lidocaine solution in 250 milliliters of D5W. How many milliliters per hour should the infusion pump be programmed to deliver this required dose? So again, we want milliliters per hour. So we'll definitely want milliliters in the numerator here at some point. Alternatively, we could also just make sure our times in the denominator. I think I want to do that instead. So we have 1.5 milligrams per minute. And then we have a solution that is 0.4% lidocaine. So what we can do with that is we can essentially multiply it. So if we know there's 0.4 grams of lidocaine in 100 milliliters, in 250 milliliters, because that's what this is stocked in, we can multiply that to figure it out. So this would be x over here. So 0.4 times 250 divided by 100. We get that there's going to be like 1 gram in each of these bags. So we can set this up as 1 gram per 100 mils, or per 250 mils, I'm sorry, because that'll still be our 0.2 or a 0.4% solution. And then we can cancel out both grams and milliliters here. 1 gram is 1,000 milligrams. So this is something that is a little more uncommon just for the setup of this problem, but it's interesting. We're actually canceling 2 units with 1 fraction, just because we don't need grams or milligrams. And this will leave us with our milliliters per minute. However, we want hours. So what we can also do is we can just do 60 minutes in an hour. And that'll finally get us with our milliliters per hour that we want. So 1.5 times 250 divided by 1,000, and then times 60. And we get that we need 22.5 mils per hour in order to solve that. Not too bad. This next one, alphenyl HCl may be administered at 1 microgram per kilogram per minute for anesthesia if a total dose of 0.35 was administered to a 115-pound patient. Calculate the number of minutes that dose should have been infused over. So for this one, it's a little interesting. We actually are going to want our minutes in the numerator. So we're going to set up this problem kind of weird again. We know that kilograms times minutes is equivalent to, I think that's 1 microgram. Yeah, 1 microgram. 1 microgram. And then we can kind of just cancel out all our other units that we don't need. So we know that 0.35 milligrams are infused. So if we do 1,000 micrograms per milligram times 0.35 milligrams, these cancel. Then we know that 1 kilogram is 2.2 pounds. These cancel. Patient's 115 pounds. These cancel. And we are left with minutes. So from here, I'm just going to plug all that in my calculator. So we have 1,000 times 0.35 times 2.2 divided by 115. And we get that this dose was administered over 6.7 minutes, roughly. So now let's talk about military time. Military time isn't that confusing, especially before like 12 p.m. because literally all it is midnight is 000. So anything between 12 a.m. and 1 a.m. is going to be written, let's say like 12:45 a.m. That'll just be written as 0045. Not too bad. And then everything else is normal, like let's say 6:45 a.m. That'll be 0645. It's important you put this leading zero, even though you wouldn't really need it in standard time. But just for the purposes of this time, that's how you write it. Afternoon, it's a little more complicated, or I should say, honestly, after 1 p.m. Because instead of looping back to 1, it's just, it's 13 now. So let's say 1:15. 1:15 would just be 13:15. It's like 1 plus 12, and that goes all the way up to 23. The highest time in military time would be 11:59 p.m. It'll be written as 23:59. And it'll never go to 24, it'll just loop back to 0. But it's just like a full 24-hour clock. This is used not only in the military, but also in hospitals a lot, which is kind of why it's taught in this course. But yeah, that's pretty much all there is with that. So let's just do a few problems with it really quick. 12,000 units heparin in 500 milliliters saline. Infuses in a patient at 1 a.m. at a rate of 1,200 units per hour. At 8:30, the rate is lowered to 1,000 units per hour. At 10 a.m., the rate is then lowered again to 800 units per hour. Approximately at what time will the solution run out? So these problems, unfortunately, they're more tedious than anything. But yeah, I'll show you how to solve them. So what we need to do is, for this, our milliliters don't matter at all because our rate's in units per hour. So this 500 milliliters normal saline, we can pretty much pretend that doesn't exist for this problem. We're just looking at units. So we know that there are 12,000 units to begin with. 12,000. And then we know our initial infusion rate is 1,200 units per hour. So minus 1,200. And since it's units over time, we can actually just kind of use our military times. So if we began at 1 a.m., 0100, and then we stopped that at 8:30 a.m. So essentially we're doing 8:30 minus 100. Remember, since these are times, we're not looking at them like we're looking at kind of standard things. You need to remember they're still in intervals of 60 minutes. So this is essentially, if we were to do like, let's say this was 8 a.m. instead of 8:30 a.m., this would be 7 times 60 because that's 7 hours. And in this case, it's, so 7 times 60 is 420. But then we're going to add another 30 because of that 8:30. It's probably the easiest way to do this. We get 450 minutes. Oh, I take all that back. There's no reason to do this in minutes because it's asking for our rate in hours. Sometimes it will ask for it in minutes. But same kind of concept, right? We know this is 7 hours between 8 a.m. and 1 a.m. Plus 30, so that's another half because 30 minutes over 60 minutes is 1/2. I know it seems super basic, but just keep that in mind. So for this, we're basically, instead of 830 minus 100, we're basically just multiplying this rate by 7.5. for those 7.5 hours that this rate went on. And when we do that, 12,000 minus 1,200 times 7.5, we get that there are 3,000 units left. 3,000. So now we do the same thing. So we do, instead of 12,000, 3,000 minus, now our rate is 1,000 units. And what's our time? 8:30 to 10 a.m. So it will be, we could write it as like 1,000 minus 830. This is just a difference of 1.5. It's that rule with half an hour again, where half an hour is, well, where 30 minutes is half an hour. I was about to say half an hour is half an hour, like duh. So this is just 1.5 here, because that's the difference in times. So if we do 3,000 minus 1,000 times 1.5, we're left with 1,500 units left. And then finally, the final part of our problem, 1,500 minus our final rate is 800 units per hour. And here's where it gets different, because it wants to know what time we're finishing at. So instead of setting it up like subtraction like we've been doing, we're basically just going to divide our 1,500 by 800, because if it's like, if you want to know the units for this, it's 1,500 units divided by 800 units per hour. Units will cancel, hours will go to the numerator. And once we do that, we get 1,500 divided by 800. We get 1.875. Now the 1 is really easy to add here, right? We could just add the 1 to 10 o'clock. This will mean it's 11 o'clock. But then we have that 0.875. So the easiest thing to do with that 0.875 is to just multiply it by 60. This will show how many minutes you need. So if we multiply that by 60, we get that's 52.5. When it comes to something like this, always round up, especially if it's only like a minute, because it doesn't really matter. So our final answer is 11:53, if that makes sense, because we're basically just changing that rate. We're trying to add all the minutes, and eventually we get to kind of the final point, which is 11:53. And since it's just asking what time the solution will run out, not like how long the solution ran, this is our final answer. But if it was asking how long the solution ran, we could also just do 11:53 minus 1, and that would be 10 hours and 53 minutes. So that's how you'd solve that. So for this next one, you begin infusing on a patient at 23:30, so 11:30 at night on February 21st, 80 mils an hour, and it's 20 milliequivalents KCl in normal saline. At 5:30 on the next day, the rate is changed to 2.5 milliequivalents per hour for 2 hours. And for 2 hours. After the 2-hour period, the original rate resumes at approximately what time will the infusion run out? So there's a lot going on here. It originally starts with milliliters. So what we can do is we can just do our initial milliliters, which is 1,000, minus 80 milliliters per hour, right? This is essentially the same in our last problem, where we were like, this is our rate. So it's what we subtract, then we multiply that by the time difference. So we have 23:30, and then that goes to 5:30 in the morning. The difference between this is 6 hours. Since this is a milliliters per hour, it's just that. And so what we find is that 1,000 minus 80 times 6, we get 520 mils are left in that bag. But now all of a sudden, our units change. We, instead of wanting milliliters now, we want milliequivalents at a certain rate. How do we do that with what we have left? Well, since we can essentially set up a proportion, since we know that there's 20 milliequivalents in 1,000 milliliters, we can find out how many are left in 520 milliliters just by setting up a proportion like this. So we'll do 20 times 520, and then divided by 1,000. And we find out that left in this bag at this time, at this 5:30 a.m. time point, there are 10.4 milliequivalents left in the bag. So with that 10.4, what we can do now is, now that we're going back into, or now that we're going into milliequivalents, we can do 10.4 minus 2.5 milliequivalents per hour. So 2.5 is our new rate at which we're running out by. And this is for 2 hours. So with that, we get 5.4 milliequivalents left in the bag. But just to make our life difficult, they have us go back into the original rate. And it wants to know what time the infusion will run out. So now we've got to do essentially the same thing in reverse. So we know that there's 5.4 MEQ per an unknown number of milliliters versus our 20 in 1,000. So if we multiply all this out, we get 5.4 times 1,000 divided by 20. With this, we get that there's 270 milliliters left in the bag. And we're going to do the same thing here that we did for last problem. We're going to put that 270 milliliters, divide that by 80 milliliters per hour. Milliliters cancel, hours goes to the numerator. We get that that's 3.375. Something else is this problem also isn't as nice to us with the times. It doesn't tell us the exact times. So we know that the rate has changed at 5:30 and that this is left for 2 hours. So our current time as of starting this is now 7:30. Because after we ran those milliequivalent doses at 5:30 for 2 hours, it's now 7:30, if that makes sense. So now basically we're adding 3 to 7:30, so now it's 10:30. And then we have that 0.375, so 0.375 times 60. We get 22.5, just round that up to 23. So our total final time is, once we add that 22.5 to our 10:30, is we have 10:53 a.m. on February 22nd. And normally the date isn't incredibly important, but since this wasn't overnight, you do need to put it. If you put February 21st or not a date, you'll be wrong. And I know it just kind of seems like a common sense thing, but it's just something you need to remember. So that'll be the final time the infusion rate will run out. And it does ask for the military time for this problem. But luckily, since it finished in the AM, it's basically just the same as normal time. But had this finished in the afternoon, let's say finished at like 2, it would be like 1400 something. So just, yeah, that's pretty much how you solve this. Just a lot of really tedious steps, but not too hard mathematically, just a lot of unit conversions. Okay, so let's finish off the last few practice problems. Luckily, since this is like concept 9, or this video goes up to concept 9, assuming Dr. Hegner's formatting is still the same, there's actually only one more video that's going to cover one more topic, and then you're completely done with everything you need to know for this class, assuming you've watched these videos all the way through. So what do we have here? We want to know the osmolarity per liter, assuming we crush up 4 of these lithium carbonate tablets. So the first way I'm going to start this, just since we have 4 tablets times 300 milligrams per tablet, we get 1200 milligrams, or 1.2 grams. And from here we can kind of go off to the races. We can just start doing some of our dimensional analysis. We've got 1.2 grams of lithium carbonate times, we do need to calculate grams per mole. We are given the formula down here, which will help us for 2 parts of this problem, both for the molar mass and for the osmolarity. 7 times 2 for the lithium, because there's 2 lithiums, plus 1 carbon, which is 12, plus 16 for the oxygens times 3. We get a molar mass of 74 grams per mole times 1 mole, 1,000 millimoles. Now, when this is put into water, the lithiums will break away, but the carbonate will stay together because the carbon and the oxygens have a covalent bond. So this will make 3 ions, 2 for the lithiums and 1 for the carbonate. Then the last thing we need to do is, in this problem, it also wanted us to make this in 100 milliliters of solution. So over 100 milliliters, but then times 1,000 milliliters in a liter, because our final answer is supposed to be in liters. When we do that, 1.2 divided by 74 times 1,000 times 3 divided by 100. Should really, yeah. Then times 1,000. I definitely just plugged something in my calculator wrong. Give me one moment. 1.2 divided by 74 times 1,000 times 3 divided by 100 times 1,000. Okay, that's better. I just got a really, really small number for some reason. But now the correct answer for this one should be 486.5 milliosmoles per liter. This next problem is a little bit complicated. I will try to walk you through it conceptually. It's basically kind of a little backwards from what we normally do. So for these, we are given that there's 5 million units of penicillin, but that doesn't really help us at all for this problem because it just wants how many milliliters the powder occupies. In this case, we never really know if this is like a 5 milliliter solution. We don't have like a final concentration, so we don't really know. We have units per milliliter and milliliters of diluent. So we're actually going to set this one up a little bit differently than we've set it up in the past. First of all, I hate working with big numbers like this. I think it's very unnecessary for problems like this, especially since we don't really ever care about the units of penicillin. It just doesn't change our answer. So instead of pretending these is like 250,000 and 500,000, I'm just going to like make these 200 and 500 for the sake of this problem. And that kind of like reasoning takes a little bit of intuition. So if you're not confident in doing that, feel free like just to not do that. You can leave it as the 250,000 and the 500,000. But since I know it's not going to affect my final answer, especially because I've already worked this problem, I already know how to solve it, I'm going to do that just because it helps me show off the math a little bit easier. So on the left side of our equation, we're going to have 250, not 250, just write the complete wrong number, 250 units per milliliter times 18.2 milliliters. But then remember, that's the milliliters of diluent that's added. So we need to do plus x, and x would be the volume of our dry powder. And the reason we really want to show our units here is because we want units on both sides. Since the units in the vial will never change, they're going to be equal on both sides. So that's kind of how we're able to set up this proportion. This is almost more of like a concentration times volume kind of problem, except that we have that extra step where we also add in the unknown of x. For this next side, it's 500 units per milliliter times 8.2, and then plus x again, because that powder is still the same, and that's milliliters. So now if we solve these out on each side, if we distribute that 250 and the 500, we get 250 times 18.2. We get 4550 plus 250x equal to 500 times 8.2, which is 4100 plus 500x. If we distribute these to both sides, we isolate x, we get 450 is equal to 250x. That's just by simple subtraction, just cleaning up that equation. So now all we can do is divide 450 by 250. We get that x takes up 1.8 milliliters in the vial. So that's 1.8 milliliters of powder. And this is interesting because usually they come out to whole numbers in this class. Don't be afraid if you do get a decimal, but be afraid if you get like a crazy decimal. Like for example, this is like 1.8, it goes to the 10th place. It's nice and round. Um, I'm pretty confident this is right. Plus, I know it's right because I've seen this problem work before and I've done this problem before. But if you were to get something with like a crazy decimal on a test, it's probably not right. Dr. Hegner doesn't want to grade that far, especially for this type of problem. So as long as your answer looks pretty clean, that's usually a pretty good sign for this type of problem. For this next one, this is a formula for 5 suppositories. We want to find the quantity of cocoa butter to prepare 12 suppositories. So already what we can do is we know we want 12 suppositories and the normal is 5. So it's like 12 total and then 5 total per like recipe if you want to show units. It doesn't really matter for this. All that matters is that like we have that ratio of 12 to 5 included in there. Basically just to show that the recipe will make more because we're making more. And then all it is, it's a simple proportion. Our cocoa butter is QS'd to 10 grams. Or not QS, but adding the sufficient amount. But we do need to subtract all these milligrams first. So if we add these up, we get that it's 725 milligrams. If we subtract that from 10 grams, I tried to line up those units correctly. I hope that makes sense. So like, this is grams now, just because we did that dividing by 1,000. So 10 minus 0.725, we get the final answer of we need 9.275 grams of cocoa butter for one batch. So to make 5 suppositories, which is one batch, so to make 12, we multiply that 9.275 times 12 divided by 5. We get a total of 22.26 grams of cocoa butter. Not too bad. Those proportion problems are usually pretty free as long as you know how to set them up. Next up is another alligation problem. I forget if we did allegations in this video or if it was in the last week's video, but this was personally a concept I struggled with at first, so I just like refreshing it in case any of you also struggled with them. Set up our little tic-tac-toe. 2% is our final. It's what we want in the middle. We have 2.5, 0.5, 2.5, 0.5. Difference between these is 0.5. Difference between these is 1.5. So we know we want a total, if we add these up, of 1.5 plus 0.5 equals 2. That means there's 1/4 of this because 0.5 over 2 is equivalent to 1/4. Same with the top. 1.5 over 2 is equal to 3/4. And then we can do from here. So we want 2 ounces. If we remember, 30 grams in an ounce, so 2 times 30 equals 60 grams. Now we can find out percent of each. So 3/4 times 60 grams is just equivalent to 45. So 45 grams, 2.5%. 1/4 times 60 is 15 grams, 0.5%. Not too bad. This final one I included. This is a special problem to me just because I remember getting this one wrong. And I thought it was pretty easy. So I do want to show you, just because you will get a problem similar to this, probably on your final exam, if not your second exam. It can be a little tricky. It just requires that you pay attention. So it's a simple kind of like concentration problem, right? We have 12% alcohol, 25% alcohol, and this much of each. And we know that the total is going to be, well, I'll get to that in a second. So 30 mils times 12% plus 30 mils times 25%. And then this last one is cherry syrup. There's no alcohol. So you could just do, the correct way to do this is to do 0% times what might be confusing on this problem is you need to remember this QS. So we need to do 90 minus 30 minus 30 to get that we need 30 mils of this cherry syrup. Some of you are probably like, duh, like that's an obvious step. This is something I missed on this problem. So I wanted to call that out just because it can be, usually when you see this type of problem, it's not a QS. Usually it's just pure ingredients. So for here it'd be 30 mils, but obviously like 30 times 0 is just 0. And then the whole thing, instead of being 150, because that's how I did it when I did this problem wrong, it'll just be 90, because that's your QS. So all this over 90. Let me run this through my calculator really quick. 30 times 12 plus 30 times 25 divided by 90. We get a final concentration of 12.3%. 33%. Which makes sense, right? We have a little bit of the 25, a little bit of the 12, and then 0. Average of 25 and 0 is like 12.5%. And when compared to like 12%, it makes sense that it falls around this range. So with that, that is everything for your exam 2. Good luck, and there should be one more video that should hopefully be a little bit shorter. And good luck. I hope you did well in the class, and if you're taking the final, I hope this is a good review for you.